Hello everyone. Today we will be discussing about algebraic structures. My name is Kautilya Chaudhary. So first we will be looking at the basic definition, and then we will be trying to understand it with the help of a composition table. Let us first try to understand what an algebraic structure is. So the definition says a non-empty set S is called an algebraic structure with respect to a binary operation star if it follows the following axioms. Closure. A star B belongs to S for all A and B belonging to S. What it means, if we have two numbers A and B which belongs to S and we apply star on it, then the resulting number will also belong to S. Now let us look at its composition table. Now this is a composition with some binary operation. As you can see that all the elements, the resulting elements are only 0, 1, 2 and 3, which are also belonging to the set S. So we can conclude that this is an algebraic structure. Now that we have understood an algebraic structure, let us move to the next, that is the semigroup. So it says a non-empty set S defined as S and star, where star is in binary operation, is called a semigroup if it follows the following axioms: closure and associativity, where associative means A star B star C is equal to A star B star C for all A, B and C belongs to S. So we can say that an semigroup is an algebraic structure which also follows associativity. So a semigroup is a subset of algebraic structure. After understanding a semigroup, the next topic is a monoid. So it says a non-empty set S, and it is represented by S star, is called a monoid if it follows the following axioms: closure, associativity and identity element. And that is, there exists E belonging to S such that A star E is equal to E star A is equal to A for all A belonging to S. That is, it means that there exists an element E such that if we operate that E and with any element, it will return the element itself. Now if we look at the composition table, we can clearly see that there exists one such row in which, or column, in which the elements are as it is as they are. Here I have marked one column, so 0 is the identity element in this case. By looking at the axioms and the composition table, we can conclude that a monoid is a subset of semigroup which itself was a subset of algebraic structure. Now next let us understand what a group is. So a group is a non-empty set G represented by G star is called a group if it follows the following axioms: closure, associativity, identity element and inverses. For all A belongings to G, if there exists an A inverse belonging to G such that A star A inverse is equal to A inverse star A is equal to E. What it means, that for each element there exists an element such that if we operate it with star, it will return the identity element, and that element is called an inverse element. Now if we look at the composition table, as you can see in each row there exists one element which returns the identity element 0, like in the first row it is 0, in the second row it is 3, in the third row it is 2 and in the fourth row it is 1. So 0, 3, 2, 1 respectively are the inverses. Hence we can conclude a group is a subset of a monoid. Now lastly, let us discuss what an abelian group is. So an abelian group is a non-empty set S represented by H star is called abelian group if it follows the following axioms: closure, associativity, identity, inverses, and commutative. Commutative means A star B is equal to B star A for all AB belonging to S. That is, let us understand it by the composition table. So if we look at the composition table, we can say that the columns and the rows are symmetric. As you can see, I have marked the second column and the second row. They have these symmetric elements. So in order to a set be abelian group, the rows and columns should be symmetric in the composition table. And we can also say at this stage that an abelian group is a subset of group which itself was a subset of monoid, which itself was a subset of semigroup, and this whole come under a broad term of algebraic structures. Thank you.